Right, so let's finish this. So I'm going to start where we left off on the last part. So this will be part two. And I'm actually still not exactly sure what happened in that last video, but anyway. Uh, so consider the following equilibrium. So we've already mentioned this. What I would like for you to look at down at the middle part of this slide is that the K and the Q are the same, except that you can't take the Q and set it equal to KSP. Only in very, very rare circumstances would they be the same. But you can't take the concentrations of the products and set them equal to KSP unless you're at equilibrium. But basically, by definition, Q is not at equilibrium, right? So it's not going to work the same way KSP does. It just has the same form. Okay, so let's go to the next slide. So we've already mentioned this. If KSP is the same as Q, we're saturated. If Q is less than KSP, then more of the solute can dissolve. And if Q is greater than KSP, then you're supersaturated somehow, and some of the stuff that's already dissolved into the solution is going to have to precipitate out. Next slide. So here's an example. In your blood plasma, you have, let's say, calcium oxalate. They're saying that we have a particular number for the concentration of calcium and for the oxalate ion. So would we expect calcium oxalate to precipitate? Okay, so, and they give us the KSP. The KSP for calcium oxalate is 2.3 times 10 to the minus 9th. Here again, we've seen this several times, is the equilibrium. Calcium oxalate breaks up into Ca2 plus C2O4 2 minus. So what's our KSP expression? Well, KSP equals Ca2 plus times C2O4 2 minus. So the Q expression would be the same, except you can't set it to equal to KSP because we're not at equilibrium. Okay, so it's important that you understand that. The Q expression is the same as KSP, except that it isn't at equilibrium. Okay, so in other words, what you want to do is you want to find out what Q is, the numerical value, and then compare it to K. So here, because this one is so easy, right, it's just 1 to 1 to 1, the Q value will just be the concentration of Ca2 plus times the concentration of C2O4 2 minus, which is going to be, and if you look back at the problem statement, calcium is 0.0025 molar, and oxalate is 1 times 10 to the minus 7th molar. So we just multiply those two numbers together, and it's done at the bottom. Q is 0.0025 times 1 times 10 to the minus 7th, and that is 2.5 times 10 to the minus 10th. So now we want to compare that with K. So look back up at the problem statement. The KSP is 2.3 E minus 9. That's a little bit larger than Q. And what that means is that since Q is less than K, more of this can dissolve. More of this calcium oxalate can dissolve. So we're before saturation. Next slide. So the value is smaller than the K, so not only will precipitation will not occur, but also we can still dissolve more of this calcium oxalate. Next slide. All right, this one a little more tricky. A student mixes 0.2 liters of 0.006 molar strontium nitrate with 0.1 liters of 0.015 molar potassium chromate. Will a precipitate form? Okay, so if you get a problem like this, either on your third test or on the final, you'll have to stop for a second, because they're not going to, well, in this case they actually did, but they wouldn't have to tell you what the precipitate would be. So think back to 1311. If you look at these two compounds, strontium nitrate, remember the rules, nitrates are always soluble. And then look at this second compound, it's potassium chromate. Potassium, again, always soluble. So what is that telling us? It's telling us that the only possible way you could get a precipitate out of these two things, if you mixed them together, would be to get strontium chromate. So that's what we're looking for. Now, they gave you the KSP for that. That's a dead giveaway that's what you're supposed to work with. But they could get around that by giving you the KSP for some other things too. Although in this particular case, there's no other way that you could get a precipitate. They could pretend, or they could make one up. All right, so the first step is to see what we're looking for that might precipitate, and then look at the K value, and then what we have to figure out is the Q value for that. So the Q will be figured out the same way as the K, but it's not at equilibrium. So we use these numbers that they gave us here. All right, so we have to figure out the molarity of strontium nitrate and the molarity of potassium chromate first. To do that, we have to find how many moles we have of each and divide both of them by 0.3 liters because that's the final volume. Once we have those two molarities, then we'll use those in our expression. So let's look at the oxidation states. Strontium is going to be +2 for reasons that I think should be obvious to you by now, and chromate will be -2. So what will they make when they come together? They'll make strontium chromate, which will just have the formula SrCrO4. No 2s or 3s in this. So it's 1 to 1 to 1. So what we want to do then, if you look at the bottom, you see that bolded SrCrO4. That's what we're going to be putting into water, or it'll be in water already, and then it will start to barely dissociate. So the equilibrium will be SrCrO4, double-headed arrow, Sr2++ CrO4 2-. So 1 to 1 to 1. So what we need to do here is multiply the concentration of the strontium times the concentration of the chromate. But these numbers here, the 0.006 and the 0.015, are not the numbers we need to use. We have to multiply 0.2 times 0.006 to get the number of moles of strontium nitrate and divide by 0.3 liters. Same thing for the chromate. And then when we do that, we'll find the concentration of strontium nitrate and the concentration of potassium chromate. But it turns out that because for every strontium nitrate that breaks up, you produce 1 strontium, also for every potassium chromate that breaks up, you produce 1 chromate, then it turns out that those numbers will also be good for the strontium 2+ and the chromate 2-. Next slide. So just go through this: 0.006 moles per liter times 0.2 liters, 0.0012 moles of strontium nitrate, divide by 0.3 liters to get the concentration, and it's going to be 0.004 molar for the strontium nitrate, but it will also be that same number for strontium 2+, yes. For the potassium chromate, 0.015 times 0.1 is 0.0015, divided by 0.3 is 0.005. So the molarity of the potassium chromate is 0.005. Also the chromate, because there's 1 for every K2CrO4, will be the same. It will also be 0.005. So all we have to do now is multiply 0.004 times 0.005. Next slide. And when we do that, we get 0.00002, or 2 times 10 to the -5th for Q. The K value, which was a couple of slides previous, was 3.6 times 10 to the -5th. The Q here is 2 times 10 to the -5th. So the 2 is just a little bit less than 3.6. So that means that we still have not reached the saturation point. So a precipitate will not form. We could actually add a little bit more of the strontium chromate. Next slide. pH effect on solubility deals with when one of the products that breaks down from the salt is the conjugate base of a weak acid, like oxalate. Oxalate is the conjugate base of oxalic acid, which is a weak acid. We can get it to shift the equilibrium to the left if we add H+. Okay, so why would we want to do that? Because that will actually, excuse me, that will shift it to the right by adding H+, because what it will do will be to produce oxalic acid, but oxalic acid is not in the equilibrium. So it will actually come out of the equilibrium, which is removing a product, which means the equilibrium will shift to the right. Why would we want to do that? Well, if one of the products is silver or gold, then obviously we want to shift it to the right to get the silver or the gold. Next slide. Next slide. So here, calcium oxalate, another one that we've used before. We've already seen that oxalate is the conjugate base for oxalic acid. At the top right in yellow is the formula for oxalic acid. COOH joined to another COOH. If we add H plus to that, it will produce either COOH, COO minus, or it could also produce COOH, COOH. Either way, it's going to produce something that is not in the equilibrium. So the HOOC-COO will come out of that equilibrium. In other words, the C2O4 minus is being removed from the equilibrium. So that means that you're removing a product, and when you remove a product, it will shift the equilibrium to the right. So therefore, that will increase the solubility. Next slide. All right, so concept check. How does the solubility of silver chloride in water compare to that of silver chloride in an acidic solution? In other words, if we do the same thing we just did for oxalic acid and oxalate, will it have the same effect if we do it for silver chloride? So look at this for a second and think about it. Silver chloride, so it will break up into silver plus and Cl minus. Are either Ag plus or Cl minus the conjugate base of a weak acid? Well, silver definitely is not, right? But what about Cl minus? So you'll have to watch this. Cl minus is the conjugate base of an acid, but it's the conjugate base of HCl. Right, so is HCl a weak acid? No. So if you add H plus to Cl minus, it will make HCl, but then it's immediately going to just break apart again because strong acids completely dissociate in water. So you're not going to accomplish anything. You're not going to make HCl and take Cl minus out of the equilibrium, right? Because HCl is a strong acid. So it will be the same as if you didn't add anything at all. So the solubility will be the same. Next slide. Next slide. Now, another question, how does the solubility of silver phosphate in water compare to the solubility of silver phosphate in an acidic solution? The answer here will be different because silver phosphate is going to break up into silver and phosphate phosphate is the conjugate base to phosphoric acid, or in this case, it would actually be HPO4 2 minus. All right, so, but regardless, it's still the conjugate base of an acid. So I guess I don't even know what the name of that is, but because it will form HPO4 2 minus from PO4 3 minus, then it will take PO4 3 minus out of the equilibrium. So it will shift the equilibrium to the right. So the solubility will be more if you add acid to a silver phosphate solution. Next slide. So here is the solubility equilibrium for silver phosphate. Silver phosphate breaks up into 3Ag plus PO4 3 minus. The PO4 3 minus is the conjugate base of HPO4 2 minus. So adding HNO3, for example, at the bottom, if you add nitric acid or HCl, the same thing, you're going to produce H plus NO3 minus or Cl minus. Then that H plus can react with the PO4 3 minus to make HPO4 2 minus. Next slide. And that is going to pull the PO4 3 minus out of the equilibrium. Okay, do you understand? So because we're removing a product, the whole equilibrium shifts to the right. That's Le Chatelier's principle. And that will cause it to just keep dissolving and dissolving as long as we keep doing that, which means that we're increasing the solubility. So adding H plus to the conjugate base of a weak acid will increase the solubility. That's one of two ways we can do that. Next slide. All right, trick question here, concept check. How does the KSP of silver phosphate compare to that of silver phosphate in an acidic solution? All right, so the solubility of silver phosphate will increase in an acidic solution for the reason we just saw, but the KSP doesn't change. Remember, the only thing that can change constants is if you change the temperature. Or, I mean, you could also change the activation energy, but that's basically not going to happen. So the only real way you have available to change a constant would be to change the temperature. Next slide. Next slide. Find the solubility of AgCl with a KSP value if you already have some of the chloride present. All right, so if we just had this as a problem, and we did earlier, right? Remember, way back at the beginning of the slideshow, we did this one already, and we came up with x squared equals 1.6 times 10 to the minus 10th. And when we solved for x, we got 1.3 times 10 to the minus 5th. Now we're going to do it again, but we're going to do it in calcium chloride. Now, is there a common ion in calcium chloride with silver chloride? Well, of course, it's chloride, right? It's in both. So we want to write AgCl, double-headed arrow, Ag plus Cl minus. That's our main equilibrium. And then we want to figure out how much chloride we have already, so that when we make our ice table, rather than to start with 0 at the top for the initial concentration of Cl minus, we'll start with what we have. How much do we have? We have 4 times 10 to the minus 3rd moles per liter. So we'll write 0.004 moles, or 0.004, in the initial slot for Cl minus. Next slide. So our main equilibrium is AgCl gives Ag plus Cl minus, and then the amount of Cl here would be 0.004 times 2, so we will write not 0.004 as I said in the previous slide. We have to multiply it by 2 because I forgot that the calcium chloride breaks up into Ca plus 2 Cl minus. So we have to multiply the 0.004 times 2, and that's 0.008. So we're going to have 0.008, and I didn't put the ice table here, but it would be 0.008 plus x would be 0.008 plus x for the Cl minus. So KSP would be 1.6 times 10 to the minus 10th. That equals the concentration of the silver times the concentration of the chloride. So for the silver, we've got 0 plus x is x. For the chloride, we have 0.008 plus x is 0.008 plus x. So write that in for the concentration of the Cl minus. Assume that x is negligible there in the x plus 0.008. So we just have 0.008 times x equals KSP. To solve that, divide both sides by 0.008, and we get that x is 2 times 10 to the minus 8th. And that is the solubility for the silver chloride. So notice here, originally in water, silver chloride had a solubility of 1.3 times 10 to the minus 5th. Now, if we add this common ion, it has actually gotten smaller because the effect is that it will cause the solubility to decrease. So just remember that when you add a common ion, it will cause the solubility to decrease. Next slide. All right, for this one, calculate the solubility of silver chloride in calcium nitrate. The KSP here is 1.6 times 10 to the minus 10th. The solubility in water is 1.3 times 10 to the minus 5th. Will it change if we add calcium nitrate? So before you do anything else, look at calcium nitrate to see if there's any common ion in calcium nitrate with silver chloride. Is anything in calcium nitrate also present in silver chloride? No. So what effect is it going to have? None. So the solubility will still be 1.3 times 10 to the minus 5th. Okay, next slide. All right, and then the other way that we can increase the solubility is to add a complex ion. And what this means is that, like if you have a product of silver plus, then you can pull that out of the equilibrium by adding something that will cause it to turn into a complex ion. What we mean by a complex ion is when you have, for example, silver plus, and it's complexed with like 1 or 2 NH3s, where this is a Lewis acid-Lewis base reaction. And so, for example, the lone pair on the NH3 will be attracted to the positive charge on the silver. And actually, for silver, it works out best if you have 2 NH3s that are complexed around it. So if you want to think of one of them as attaching from the top and one from the bottom to make like a cage around the silver, that's actually what happens. And it's most stable when it has exactly 2 NH3s. So it seems that silver is best complexed by having one on the top, one ammonia on the top, and one on the bottom. Okay, so what that does, though, it's the same thing that happened when we added the acid to the conjugate base of a weak acid. It reconstitutes the weak acid and pulls the conjugate base of the weak acid out of the equilibrium, so you're removing a product. Well, that's the same thing that's happening here. Next slide. Next slide. So, for example, if we have silver plus and we add 2 ammonia molecules to that, it will produce silver with 2 ammonias complexed around it. So, next slide. So a few definitions here. The ammonia that we're adding is referred to in coordinate complex ion equilibria as a ligand. That's at the bottom. Ligand is something that you add to, like, for example, silver plus, that will make a coordinate complex ion. So a ligand is like, for example, the NH3. The complex ion would be the whole thing that has the silver plus with the 2 NH3s around it. And the complex is also the same thing. So next slide. So again, we have it in 2 steps here. So first they're showing silver plus NH3 produces AgNH3 plus, and then another NH3 would add to that to make AgNH3 plus, and so the overall reaction would be Ag plus 2 NH3s gives AgNH3 2 plus. Next slide. Next slide, because this one has 2 parts. So again, at the top we have the same thing, the formation constant. So here's another kind of a constant. The formation constant is K sub F. And that is what the constant would be for the formation of AgNH3 from Ag plus 2 NH3. And that expression would be the products over the reactants. So this is not a KSP expression. So in this case, you would also have something on the bottom in the denominator. It would be AgNH3 plus over Ag plus times NH3 to the 2nd power because of the 2. All right, so this is a KF expression. There's one other one that's called the KD expression that we're not going to worry about, and that would be to take the AgNH3 2 and dissociate that, but we're not going to worry about that because it's not really necessary. All right. So we're going to do a lot more with this expression. One of the work problems that we'll do for this chapter will deal with this thing at the top, this equilibrium. Ag plus 2NH3 gives AgNH3 2. We'll need to know what the formation constant is for this, so we'll deal with this again later. So I think there might be one more slide here. I'm going to click. The value here for the AgNH3 2 is 1.7 times 10 to the 7th. That's the formation constant. All right, next slide. I believe this is the end of this, and if it is, I'll see you in the work problems. Okay, one other thing. The very large value means that the complex ion is quite stable. In other words, it means that it goes all the way to the right. So for silver plus, you will have the most stable complex ion by adding 2 NH3s. Next slide. So there are two strategies available for dissolving a water-insoluble ionic solid like silver plus or like oxalate. So for oxalate, if it is a good base, because it's the conjugate base of a weak acid, then we can increase its solubility by adding H plus in the form of either HCl or HNO3 or something like that. The second possibility would be like if you have a product like silver plus, you can increase the solubility of that, but you use a different technique. You add ammonia or some other ligand to make a complex ion. And that is the end of this chapter. Next slide. So I will see you in the work problems.